And now I would officially like to introduce you to today's presenter, Dr. Martin Cross, Senior Lecturer at Edith Cowan University. Martin began his career as a toxicologist working in the UK chemical industry. He has an honours degree in toxicology, a Master's of Public Health, and a PhD. Martin was an occupational hygienist for WorkSafe WA and an occupational hygienist for WA Department of Health. He is now a senior lecturer at ECU with a teaching and research role in postgraduate occupational health and safety. Martin's expertise and skills span many aspects of occupational health and hygiene. With over 35 years of a variety of industry experience, we couldn't find a better presenter to present on this topic of toxicology. So Martin, may I please request you to switch on your webcam and microphone and lead the session for us.
I believe I've got connectivity now. Hopefully you can hear me. Yeah, okay, good. We had some connectivity problems this morning, but we've got to overcome those. So yeah, thank you for attending this lecture on the importance of toxicology to occupational hygienists. I've called it Toxicology 101 because it is basic toxicology. But hopefully it's useful to us occupational hygienists. So what I'm intending to cover in this session is the general, okay, I had something covering my slides, it's now gone. I intend to cover general occupational toxicology considerations, absorption, distribution, biotransformation and excretion of toxins, and then some briefly on toxicology of organs and systems, some health effects of hazardous substances, and then hazardous substance encountered in the workplace. So what is toxicology? It's derived from the Greek words toxikos and logos. It's the study of poisons. It's the science that deals with poisons or toxicants and their effects. Toxicants may be natural or man-made. It's a science that's evolved from ancient poisoners, and I'm going to give you a brief overview of a couple of those. Socrates in 470 to 399 BC, he was executed by drinking a solution of hemlock. The actual potion major ingredient being piperidine alkaloids. So yeah, over history, we've learnt from poisonings. Another famous family, if you like, the Borgias, used a potion of chemicals to kill their political rivals. In this, their favorite potion was arsenic. You can see a painting there, and you can see the glass of wine that's being fed to the Pope Alexander. The Borgias used to use poisons to kill off their rivals. More recently, there's an attempted assassination by using ricin. There was a lady that sent ricin-laced letters to President Obama. And I believe, yeah, more recently it's happened again with Trump. So ricin is a poison that's found naturally in castor beans, and it only takes milligrams per kilogram to be highly toxic. And again, a recent event was the Russian military officer. He was a double agent. There was an attempted poison with Novichok nerve agent, which is a toxic organophosphate. Yeah, the English are still doing a bit of detective work on that. Going to some disasters, chemical spills, if you like. One very famous one was the Minamata disease. It occurred in Minamata Bay. A local factory was pumping mercury waste into the bay. And initially, it was noticed that cats were running around and convulsing and running in circles, going mad, basically. Then it was noticed in humans. They had slurred speech and convulsions and started to die. And it was a neurological syndrome caused by severe mercury poisoning. What happened pumping into the bay, the actual inorganic mercury got biotransformed in the ecosystem to methyl mercury and it got into fish and shellfish, and then it was consumed by humans. So a couple of disasters. Another one was in 1976. There was an explosion in Seveso in Italy, and it exposed people in the factory and people locally to dioxin. There were many chloracne cases were diagnosed in the residents, especially in children. There's a photograph there of what chloracne looks like. So it was TCDD, which is dioxin. It's associated with decreased male and female fertility, and that occurred in Seveso. And it also is a carcinogen and caused cancer in those victims. Another one that occurred in '84 was there were 40 tons of methyl isocyanate gas that leaked from a pesticide in Bhopal in India, and it immediately killed at least 3,800 people, and it caused significant morbidity and premature deaths of many thousands more. And the issue is still continuing today. The facility continued to operate with safety equipment and procedures far below the standards found in its sister plant in the USA. There were financial reasons for that. They weren't operating the plant correctly. So people got exposed with methyl isocyanate, which is a carbamate pesticide. Again, natural versus man-made toxic substances. One of the most toxic, if not the most toxic, is botulinum toxin. It's a neurotoxin produced by the bacterium Clostridium botulinum. This bacteria is found in soil and it can survive and grow under certain conditions. Historically, it was found in food that was improperly canned. If you remember, the old cans used to be made out of tin, and they sort of the metal lapped over, and the seal could easily break open. And this telltale sign was bulging cans, and quite often it could be a buildup of the botulinum. As you probably aware that Botox is used, it's actually used for cosmetic reasons to basically smooth out the wrinkles in people's faces. Another natural one is aflatoxins. They're a natural occurring mycotoxin that are produced by many species of Aspergillus flavius, and it's a fungus. And the aflatoxins one of the most potent carcinogens around. It can occur in moldy peanuts. First, I think it was when it was moldy peanuts were fed to, I think it was turkeys, and I think it was in Turkey. Turkeys ended up with liver tumors, and that was when it was first noticed. It can occur in peanut butter, but obviously it's been screened, and obviously the levels are very low, and it's not a significant problem. The FDA or the Food and Drug Administration people are constantly surveilling that. Another natural poison is strychnine. It comes from the strychnine tree, which is an evergreen tree. So it comes from the plant Strychnos nux vomica, an indigenous tropical and subtropical climate plant. Grows in abundance in Southeast Asia, and it also grows in Australia. So, yeah, strychnine, as you are aware, is pretty toxic. The first, for going to occupational toxicology, there was an issue with scrotal cancer in chimney sweeps, and it was found that benzo-alpha-pyrene was the first recognized occupational associated cancer of scrotum cancer suffered by chimney sweeps in the 18th century. And this was identified by Sir Percival Potts in 1775. And it's from the Sutton coal tar that they used to send young boys up chimneys to sweep out the chimneys, and quite often they were usually naked so they didn't get soiled clothes, and they ended up with scrotal cancer. And benzopyrene, as you're probably aware, is a polycyclic aromatic amine. So we have our first prompt question. I think Samira is running a poll behind the scenes there, but the first question is, natural chemicals are less toxic than man-made chemicals. Do you believe that to be true or false? Polls are coming through. Yeah. Most of you got it right. I can see that over 90-odd%, 96, are voted that it is false, that natural chemicals are not, as you're probably aware, if you go back to the previous slide, I mentioned that botulinum toxin, which is a natural toxin from a bacteria, is probably one of the most potent toxins out. And another one, aflatoxin, which is from moldy peanuts, is also very toxic. So the answer is false, that natural chemicals are not less toxic than man-made. Okay, so moving on. So classification of toxic agents. Toxic agents can be classified in many different ways. It can be due to the target organ. Once the toxic agent can get inside the body, and we'll talk about that a bit further on, the target organs in the body can be things like liver, heart, brain, etc., etc. So a target organ, they can be classified due to where the toxic chemical hits. It could be based on usage, solvents, pesticides, etc. It could be based on the source. It can be man-made, anthropogenic, animal, fungal, plant. It can be based on types of health effects, things like asphyxiants, carcinogens, mutagens. It can be based on physical state, whether it's a gas, liquid, or solid, or dust. It can be based on chemical stability or reactivity, things like flammability, etc. Chemical structure, things like halogenated hydrocarbons, aromatic amines, so based on chemistry. And also it can be classified on the potency of the poison, from slightly toxic, moderately toxic, to highly toxic. So looking at the potency, I've got a slide here with relative toxicities. We mentioned botulinum. If I start at the bottom of that table, botulinum toxin, as you can see there, this is in milligrams per kilogram. These are what are called LD50 values in rats, given to rats orally. and it gives a reflection of how toxic these chemicals are. So botulinum toxin, as you can see there, it's 0.401 milligrams per kilogram in rats, and it causes 50% deaths in rats at that level. Then you've got dioxin going up the table. Again, a very low dose that will create toxicity. Sodium cyanide, strychnine there, and then we start going into things like paraquat is a herbicide. That's 120 milligrams per kilogram, and even going up to ethanol. Some people try to kill themselves with binge drinking, but it takes a fair amount to cause toxicity at 7,060 milligrams per kilogram. So that's the relative toxicities. Yeah, those were based on the LD50. That's becoming an obsolete sort of test now. It's the medium quantity or lethal dose of a chemical that is estimated to kill 50% of those organisms under test conditions. Toxicology tests are invariably done in animal tests in rats and mice in the main. But for humane reasons, there are now alternatives to the oral LD50 test that are now being used. And there's a reference there to for that. And there are alternatives to animal tests, which I used to work in. Yeah, Paracelsus, a good mate of mine. He lived from 1493 to 1541, and he's sometimes called the father of toxicology. He was the first to recognize that all things are poison and nothing is without poison. Only the dose permits something not to be poisonous. And then substances often considered toxic can be benign or beneficial even in very small doses. I think one of the examples in that previous slide was vitamin A. You can get hypervitaminosis, but you can get doses that are beneficial to the body. So toxicity, you can have what is called acute toxicity and chronic toxicity. Toxicity is the intrinsic property of an agent to adversely affect an organism. So it's intrinsic property of that particular chemical or hazardous substance. You can have immediate, what are called acute toxicity, which appears immediately or shortly after a single exposure. Then you can get delayed or chronic toxicity that occurs after a lapse of some time, i.e. many months or years to become a recognizable disease. Yeah, a lot of people in safety field focus on the injuries, things like broken arms, broken legs, but you're probably aware that illnesses can take years to appear, clinical signs, and it's at great cost to the community. I've pulled this out of my master's thesis. Basically, you can have a continuum of toxic effects. You can have very early effects. You can have subthreshold levels where a chemical, this is an example of lead, where a chemical doesn't affect after a threshold level, and we'll talk about that. Then you can start seeing signs of toxicity. With lead, you obviously get an exposure. If you look at the axis on the bottom there, you've got blood lead levels at the bottom, running. If you looking at it in micrograms per 100 mil, in that bottom, you've got 0, 20, 40, 60, 80, 100. As the dose increases, you're exposed. It's absorbed into the body. The first signs are inhibition of delta aminolevulinic acid, and that can be picked up. It hits the the blood system, the heme synthesis, and one of the first signs is inhibition of LA delta amyloidic acid. Then it starts to affect more the system, hitting the hemopoietic system. You get an increase in free erythroporphyrins, and then as you go along that continuum, as the dose increases, you start to see clinical symptoms, things like constipation, abdominal pain, and then the more pronounced toxic effects, it can cause hit the peripheral nervous system and get things like wrist drop, and eventually, if the dose is high enough, you can get encephalopathy, which is the central nervous system. It can hit the brain. So, basically, with a chemical or a toxic agent, you can have a continuum of effects. Right the way through to clinical manifestations. Okay. So the role of an occupational toxicologist is the same as hygienists. The main purpose of occupational toxicology is to protect the health of workers. So we're in the got the same principles. It's about recognizing workplace exposure that may affect worker health. And the main aim, of course, is to prevent this. I'm obviously not going into control now, but talking about the basic toxicokinetics. But understanding the toxicokinetics and the toxicological information, this will help hygienists be able to predict what can happen. And okay, so yeah, the hygienist job is to try and work out where there is possible exposure, and you need to understand the pathways of occupational exposure. This slide shows that they're every stage of the product life cycle, from extraction of raw materials through to ultimate disposal. It can release toxic agents into the environment. And this little diagram shows raw material extractions, things like mining can release toxins. Obviously, manufacturing and production, if people are using lots of chemicals, for example. Even in distribution, a very simple example in distribution, it could be that vehicles, carbon monoxide from vehicles could affect people. And then you've got use and reuse, and then recycling. So people can be exposed in the product life cycle. And so, yeah, application of your occupational hygiene principles. You're probably aware: anticipation, recognition, evaluation, and control. The anticipation is a lot is through experience. What toxic chemicals can be emitted at those particular stages. It can come down to experience. It's possible to go to other resources. You can look at toxicological databases, websites. Safety data sheets are useful. There are some limitations there. When I started off as an occupational hygienist, I obviously was new. Obviously, I'd done toxicology, but I used to turn to experienced hygienists to ask them, and chemists to ask them if there was a process, what sort of agents can be produced during processing. So anticipation, even before you go to a workplace, you can SWOT up and anticipate what the toxic chemicals can be produced from the different parts of the product life cycle. And then recognition, knowing the hazards and the process itself. Yeah, go to the workplace and do proper walkthroughs and get information from people that know the process. Moving on, sorry, my computer's okay. That's right. Something was masking my computer then, I apologise. So evaluation, hygienists obviously go out and measure exposures, and then we compare them with standards, occupational exposure standards. And toxicology can help with establishing those occupational exposure standards so that we can then go off and assess the human health risk. And obviously, eventually we need to be able to advise on the control. So yeah, going to the basics of toxicology and hygiene. How can chemicals or hazardous substance get into the body? Routes of entry into the body. Yeah, before a hazard can affect an individual, it must firstly make contact with and then enter the body. And the 4 routes of entry, as you're probably aware, are inhalation. Inhalation is probably the major route of exposure in workplaces. Direct contact with the skin and then absorbed through skin. Ingestions, less, it's rarer. An injection is even rarer still. So let's look at those. So yeah, inhalation is the most common route. Things like breathing in gases, vapors, aerosols, mists, fumes, fibers or particulates. What's important to know, if you know your physiology, that if your interface between your lung and your circulatory system, when you actually get down into the alveolar parts of your lung, that they're about 1 cell of lung tissue and 1 cell of the blood capillaries that are going through the. So if it's a very thin barrier, if you like, 1 cell of lung tissue and 1 of blood tissue. So some toxins can actually get across that 2 cell wall and through into the circulatory system, into the body. An example I've given there is hydrogen cyanide. It's rapidly absorbed through the lung cells into the circulatory system, and it affects the CNS, causes loss of consciousness and even death. So inhalation is the first route of exposure. The next one is skin. It's the next most common route of exposure. Yeah, absorption through the skin depends on the concentration and solubility of the chemical. It depends on the condition of the skin, whether it's intact or broken. So if you've got wounds, it can probably get through the skin, through the epidermis and into the dermis. Chemicals such as solvents are easily taken up through the skin, which may cause systemic toxicity. And that's hence one of the reasons we have the skin notation in conjunction with the occupational exposure standards. Some chemicals can be breathed in and can also get through the skin, so you've got a double whammy there. So our occupational exposure standards here in Australia usually have a skin notification in addition to the occupational exposure standard. Rare is ingestion. So mouth contact with contaminated hand or item. I've, as a hygienist at a processing plant that I was at, we had a vanadium catalyst. It was a sulfuric acid plant, and to make sulfuric acid, vanadium pentoxide is used as a catalyst in the and basically it's a bed which sulfur dioxide is diffused through, and it helps in the production of sulfuric acid. I was the hygienist, keeping an eye on the guys that were doing this catalyst change out. The guys had all the appropriate PPE, doing the right things, but then one of the gentlemen just was disappearing around the corner, smoking cigarettes. So what we had was a increase in the urine, vanadium in the urine, because of this hand-to-hand mouth contact. So it's all about personal hygiene. This guy did have some clinical symptoms because of that. Another one, we did biological monitoring for nickel in urine, and we noticed a high level when we traced this back. There was a gentleman that was rolling his own cigarettes, and it was the personal hygiene again. He wasn't going washing his hands, going off, rolling his own cigarettes, smoking them, and got a high level of nickel in his body. Okay. Injection is even rarer. Contact with contaminated needles or sharp instruments could inject chemicals into the body. It's usually accidental injuries, which are very rare. Probably the only one that I'm aware of, probably one of the major ones, is hydraulic fuel under high pressure it's very nasty event. The hydraulic fuel can get underneath the skin, and it's quite a nasty repercussions of that. Then we can have we can actually have local effects or systemic effects. Local effects of certain chemicals exert their effects at the site of first contact. So things like acids and alkalis. If you splash an acid on your skin, you're going to get a local inflammation and a local effect. Systemic effects occur after a toxicant has been absorbed. Excuse me, again, something's come over my screen, so I can't see my slide. Oh, there we are. Systemic effects occur after the toxicants have been absorbed and distributed systemically inside the body. So, yeah, as I said before, particularly for inhalation, it can get through that's the lung parenchyma into the circulatory system, into the body, and it circulates around into the body. Okay, we've got a test your knowledge quiz again. Testing your knowledge on what's the difference between acute and chronic toxicity, and we have 3 choices there. Different organs are involved. Acute toxicity appears shortly after exposure, whereas chronic toxicity may take months or years. Or acute toxicity is less likely to lead to death than chronic toxicity. So, yeah, virtually everybody's got that one right. Acute toxicity definitely is, it appears shortly after exposure. Acute toxicity, you can actually have fatality because the dose is really high, but it appears shortly after exposure, or you can actually have subtle effects with acute as well. But with chronic toxicity, it's a build-up. You could be working in a workplace, getting constantly exposed to a toxic agent, and it can take months or years before it manifests itself. Okay, that's good, 100%. So, yeah, looking at basic toxikinetics, it's a combination of things. The effect of a hazardous substance is dependent on the concentration of the hazardous substance present in the body's systems, and it is dependent on the rates or kinetics of the absorption, distribution, metabolism, which is also biotransformation as well. So absorption, distribution, metabolism, elimination, and it's toxikinetics is a study of combined of all those processes and the passage through the body of the toxic agent or its metabolites. So let's look at absorption. Yeah, absorption can occur through basically hazardous substances get across the cell walls into the internal body system. A couple of examples there. Passive diffusion is where you've got a concentration gradient and it passes across the concentration gradient, and that's called passive diffusion. And then we have what's called active transport, which needs energy to get it across the membrane, if you like, the cell wall. Usually involves ATP, adenosine triphosphate, and then we've got phagocytosis, which is engulfment of particles that gets engulfed inside across into the body cells. And then pinocytosis, which is liquid engulfment. So those are three ways that the chemicals can be, once they've entered the body, to get into the body, they have to get across cell walls and become systemic. And then we have distribution. Once the hazardous substance has entered the circulatory system in the blood, it's distributed around the body. And this is dependent on a variety of factors. Obviously, the blood flow, the amount of blood and how fast it circulates around the body. Most toxicants bind to the plasma protein in blood. So it's the plasma protein binding has an effect of distribution around the body. It's the ability of to cross the blood vessel walls and cell membranes. And then after that, affinity of target organs. So this is where you get selective target organ toxicity. So once it's absorbed and distributed to various parts of the body, many toxicants undergo biotransformation or metabolic transformation. This biotransformation is catalyzed by several enzymes in the blood and tissues, with the aim to increase their water solubility in order to facilitate their elimination from the body. So either excreted in the urine or the feces. Okay, so biotransformation is the process that alters the physico-chemical properties of a hazardous substance away from its lipophilicity, and lipophilicity is fat loving, if you like. So it's moving away from its lipophilicity that favors the initial absorption of the hazardous substance into more water-soluble forms, namely hydrophilicity that favors elimination in the urine or feces. I've got a footnote there. While it's considered that biotransformation predominantly deactivates toxicants to their non-toxic form, and that's to protect the body, it is possible that non-toxic substances can be bioactivated. So a non-toxic substance can be activated into a toxic substance. That's used in pharmacokinetics or for drugs. They might put a drug into the body and it's bioactivated to the active drug. So biotransformation occurs in two phases. We have what are called phase 1 reactions, usually followed by phase 2 reactions. So we get uptake in the body. Then we have phase 1 biotransformation, which creates phase 1 products. They may be more water soluble, and then it goes into phase 2 biotransformation and you get phase 2 products, and then ultimately excretion. Looking at phase 1 biotransformation, there are three main phase 1 reaction types: oxidation, reduction, and hydrolysis. As an example there of an oxidation, oxygen is incorporated, and the example we're using is alcohol is metabolized primarily by two enzymes, alcohol dehydrogenase and alcohol aldehyde dehydrogenase. These enzymes help break apart the alcohol molecule making it possible to eliminate it from the body. And you can see a schematic below there. You've got alcohol dehydrogenase, you've got cytochrome P450 that helps catalyze that. And it's there's an oxidation process that goes to acetaldehyde, and then aldehyde dehydrogenase catalyzes it to acetate, making it more polar. And then goes to biotransformation. Why phase 2 biotransformation? When phase 1 reactions are not producing sufficiently hydrophilic, water-soluble or inactive metabolites, it then goes into phase 2. The toxicants or metabolites formed from phase 1 reactions undergo phase 2 reactions. These are capable of converting metabolites to more polar and water-soluble products. These enzymes that catalyze conjugation reactions are called transferases, and they're mainly found in the liver, and to a lesser extent in the intestines and other tissues. And here's an example of phase 2 biotransformation. It involves the addition of endogenous hydrophilic group through sulfation, acetylation, methylation, glutathione conjugation, and glucuronidation. And there's an example there of benzene going through phase 1 to phenol, and then with this phase 2 biotransformation, going to phenyl sulfate. So another quiz question for you on biotransformation. Biotransformation always results in reduced toxicity of the xenobiotic, which is the hazardous substance, always reduces the toxicity. It may result in detoxification or bioactivation, or has no influence on the toxicity of the xenobiotic. And looking good, yeah. Everybody is getting that answer right. So yeah, the answer is may result in detoxification or bioactivation. Okay, moving on. So target organs, I mentioned that before. Once the toxicant can get into the system, circulatory system, the systemic effects occur after toxicants have been absorbed and distributed systemically inside the body, so they circulate around the body. The toxicants, if not fully detoxified through biotransformation, can adversely affect specific organs of the body. So there are different affinities for different toxicants. Some can hit multiple target organs, others very specific ones. And here's some hazardous substance encountered within the workplace that affects target organs. Starting from the top, lung, obviously asbestos can hit the lung, things like cigarette smoking. Skin, we already mentioned that dioxin can cause chloracne of the skin, but there's some other examples there that affect the skin. Then we've got the liver. We've got things like carbon tetrachloride, methylene chloride. One interesting one there is vinyl chloride. Vinyl chloride monomer was first noticed to cause angiosarcoma of the liver. A group of guys were cleaning out the tanks in a plastics factory where vinyl chloride monomer, they got exposed, and it's a very rare tumor, angiosarcoma of the liver. And it was noticed because it's a very rare tumor. I believe at one time that they were actually thinking of using it as an anesthetic. So fortunately, it was picked up because of that very special type tumour that's very rare. So fortunately that was picked up before it could cause any further problems. Looking at the kidney, cadmium, lead, mercury. In the kidney, if you notice, there's mercury mentioned as a target organ for mercury. That's mainly inorganic mercury. If you move down to the neuropsychological, you'll also notice mercury's in that list of. Inorganic mercury tends to hit the proximal tubule of the kidney, very specific, whereas the methyl mercury, organic mercury, actually hits the central nervous system. So there can be some very specific target organs. One important feature of toxicokinetics is the half-life, the Tia half. The half-life of a xenobiotic refers to the time taken for the quantity of the xenobiotic, the toxic agent in the body, or the plasma concentration to be reduced to half of its original level through the body's elimination processes. Obviously, the half-life is reflective of the time a xenobiotic spends within the body. And obviously, the longer the toxic agent remains in the body, the more likely its toxic effect can be exacerbated. And conversely, the shorter the half-life, the less time spent in the body, the toxic effect is likely to be smaller. So half-life is looked for. One of the most important fundamentals is the dose response. The dose response relationship is the most fundamental and persuasive concept in toxicology. Generally, the higher the dose, the more severe the response. The dose response relationship is based on observed data from it can be gained from epidemiology, so effects on humans, accidental exposure or clinical, animal studies, and usually can be supplemented by in vitro, sort of in test tube type studies, or in silico, which is computer simulated, looking at the chemical structure in through computers. So the dose response, what we're looking at with the dose response is we're looking for where there's no effect, where a chemical can be safe. As you can see, the dose response curve down to the left, you've got dose on the bottom axis there, and on the vertical axis you've got the response. It could be any toxicological response. It could be fatalities, or looking more for more subtle changes in the body, and we're looking for that effect of the toxic chemical and the response. As you can see, the graph, the sigmoid shaped graph, as the dose increases there, you've got a scale 5, 10, 15, 20, 25, 30, 35. As the dose increases, the response increases, but until you get 100% response. It's usually a sigmoid curve, and what we're looking for in toxicology is we're looking for that no observed adverse effect level, the no AL. If we can predict that, we can predict the safety of the particular hazardous substances. Also, another factor that's important is the low observed effect level. They're important in conducting health risk assessments and determining occupational exposure standards. Yeah, studying the dose response is fundamental in determining safe and harmful effects of workplace chemicals. The shape of the curve itself, and looking for that no effect level, So the extrapolation of data from experimental animal studies is based on the dose-response curve. It's commonly used in human health risk assessment in the absence or in conjunction with human data by regulatory authorities. The no AEL is used and extrapolated, allowing for species difference and uncertainties. Obviously, extrapolating from animals to humans, there needs to be a safety factor. And the uncertainties of the human variability. So eventually there's a determined safe level. So yeah, and no effect, no observable effect level is used to extrapolate, allowing for species differences and uncertainties such as human variability to determine safe levels. Usually a factor of something depends on how robust the tox data is, but a safety factor of something like 10 or 100 is used to determine occupational exposure standards. There's a thing called uncertainty factors that are taken into consideration on how robust the data is. Currently, Safe Work Australia is evaluating the workplace exposures for airborne contaminants based on the dose response concept. And this is obviously dependent on the robustness. Quite often there's a sparsity of data, the robustness of the tox data, which makes it difficult to put forward a occupational exposure standard. But the toxicologists are working on that and hopefully doing a grand job. So this is the last quiz. The no observed adverse effect level is the lowest dose at which there is no observed toxic or adverse effect, or the highest dose at which there was no observed toxic or adverse effect, or the highest dose at which there was an observed effect. This is more tricky. Yeah, most people are getting it right, but it's almost a play on words, I guess, here. But yeah, it's panning out. Yeah, most people have got it right, but it is the highest dose at which there was no observed toxic or adverse effect. So you're looking at the largest amount that you can expose animals to, or and then looking for a toxic effect. So it's the highest dose at which there was no observed toxic effect. Okay, you've done well. So that was my there are some references to this. Thank you for listening. That was Toxicology 101 for occupational hygienists. Thanks for attending. I'm pleased that there was quite a number of you listening in. I'm pleased for that. There are some references there that I base my talk on. They're available there for you. If you've got any questions, I'm willing to field those now. Samara was looking out for any questions.
Hi, Martin.
Hi.
That was fantastic. I think there were many requests and many questions. So if you don't mind, we're just going to go through a few of them as time permits. So Alan asked, he's interested to know which is most significant from smoking: inhalation exposure due to fume from burning the contaminated dart, or ingestion from the dirty hand to mouth?
Oh, from smoking.
Yeah.
That example I gave you was nickel nickel being on the skin and the nickel being transferred when the person puts actually rolling the cigarette itself and getting the nickel dirt on the or they have like a tissue paper, don't they? So actually the tissue paper in the cigarette itself, nickel getting onto that, but also putting your hand, which is dirty with nickel, actually to your mouth and ingesting or swallowing nickel. If you're asking whether it's whether inhalation of cigarette smoke, smoke itself, tobacco smoke itself, obviously inhalation through the lung is going to be the more significant effect. There may be some residual on the fingers from people smoking, but the significant effect, if you're just looking purely at cigarette smoking, it's the inhalation of the smoke. But from the point I was trying to make there was poor hygiene with the vanadium example I gave you, and the nickel example was the actual workers were getting contaminated hands, not washing their hands, and then smoking and effectively touching their mouth with their dirty fingers, and then ingesting the actual chemical, which was in those two examples I gave you was vanadium pentoxide and nickel. Okay.
Coming in, and I'll take as many as I can.
Yep.
But Christopher's asked, what uncertainty factors are SWA using in their evaluations?
I'm not fully aware of all of them, but obviously there's always an uncertainty factor from extrapolating from animals, so rats and mice to humans. That's an uncertainty factor. Uncertainty factors would be the robustness of the actual data. With some of the chemicals that the toxicologists be looking at, there may be, they do weed out the poorer toxicity test, but they may not be the appropriate tox test. For example, the airborne contaminants, which the occupational exposure standards are based on for airborne contaminants, obviously inhalation is the route of exposure. But you may not have sufficient information on inhalation. You may have a feeding study, for example, or an oral study. So you've got to try and extrapolate that sort of data. And obviously there's some uncertainty factors there is a process for that. It's not just best guess. The guys do go through a very formal methodology to take into those considerations.
Okay. William asks, how do you think the industry will cope with some of the recent waste reductions? How do you think hygienists should be focusing on this re-advice and control?
Oh, dare I answer that? Oh, it's going to be difficult. Yeah, you're going to get, you've got the silica, you've got another one, formaldehyde's been dropped from, I think, or proposed from 1 down to 0.1, I think, off the top of my head. It's the practicalities of those. I don't want to really comment here. Probably not for me to comment, but yeah, it could be difficult in some workplaces to actually achieve some of those very low occupational exposure standards. That'll come out in the wash. Yeah, I don't really want to comment on that. I've got my own perception on that, but
that's okay,
yeah.
Martin.
Yeah.
There's a few more coming. I'll just take the last two, and then we'll try and wind it up. Is What is the best way to determine health effects for mixtures of chemicals, especially where the majority of the constituents are non-hazardous with low concentrations of hazardous substances?
Yeah, there are. Most of the toxicology is based on usually on the pure chemical. You can have technical grade products, and then you can have mixed exposures as well. There are formulas for looking at mixed exposures, and obviously what you're looking at in toxicology is if the mixed exposures, if the toxicokinetics are the same for those chemicals, then you're going to have at least additive effects. So you have to take that into consideration. So if both chemicals in a mixed exposure, they could be both solvents and could both affect the liver. There are methods for determining that. Any other questions, Samira?
It is, what tools are available to the modern toxicologist for new chemicals without a history of occupational exposure, and where animal studies are becoming less common for ethical reasons?
Again, yeah, obviously there's yeah, I spent half my tox life. I began in the pathology department and then moved into the genetic toxicology department, and we were looking at alternatives to animal testing, and there are some in vitro tests, and we developed a battery of tests to try and they were fairly successful in predicting effects. Could you remind me of the question again? Yeah, there are new chemicals coming on board that's yeah, anything the regulatory tox, you've got regulatory bodies that are anything that has to go out into the market, be it food products, be it agrochemicals, pharmaceuticals. There is a strict regime. Have to go through a series of toxicity tests where possible. So to get through those regulatory authorities like the FDA, EPA in America, there are strict test methods that have to go through before they can actually get out on the market. I was when I worked in the tox, I'm going back about over 30 years now, but we used to have to stick to very strict protocols and go through a range of specific animal tests or alternatives that have been approved by the regulatory authorities. So there is a screening system before they actually get out into the market.
Fantastic.
Hopefully that, yeah.
That's great, Martin. Thank you so much on behalf of everyone. A mini wave in the celebration of you at the moment. But thank you everyone for taking the time to attend the session. And Martin, there are several requests to do a session 2. So I'm going to bribe you with chocolate in the right dosage to get you to do another session for us soon. But
so
that concludes.
More than a 101.
More than a 101, please.
Yeah.
But thank you everyone. And thank you, Martin. That concludes this presentation. Have a lovely afternoon and a good weekend.
Thank you everyone for attending. Thank you.